On September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time in human history. We all know that these observations are really small, and this was a really big discovery. But do we truly understand how small these measurements were, or how important these discoveries are? Our story starts 1.3 billion years ago. The first primitive forms of plant life are just starting to evolve on Earth. Meanwhile, insanely far away, way beyond our local galaxy superclusters, two huge, possibly primordial, black holes collided. Here's a simulation I created in Universe Sandbox 2. Please note that this simulation is actually slowed down and that the two black holes were orbiting at a rate of many orbits a second. The collision of the two massive black holes converted 3 solar masses from matter into energy, sending massive gravitational waves into space. In other words, an amount of matter equal to 3 of Earth's suns was converted from matter and transformed into gravitational waves. These gravity waves radiated out into space, getting weaker and weaker as it crossed more and more space. Billions of years later on Earth, in 1916, famous scientist Albert Einstein theorized the existence of gravitational waves, though he had no way to prove they exist. An intense gravitational disturbance can create ripples in space-time in a manner similar to a rock creating ripples in the pond. These ripples spread out and become less visible as they cross distance. Two black holes colliding violently jostle space-time, and the effects can be detected light years away. So on September 14th, 2015, the wave finally reached Earth, and a record-breaking earthquake occurred and everyone on Earth died! Just kidding. The disturbance was so minute our ordinary senses and instruments could not detect it. But LIGO could. LIGO works by sending out 2 laser beams perpendicular to each other. The lasers are reflected off mirrors 4 kilometers away and bounce back to the detectors, where the total distance is measured very precisely. If gravitational waves pass through the detectors, space-time becomes distorted, and one of the lasers will be shortened while the other one is lengthened. LIGO detects the difference, then compares it with its other location, to make sure they were detecting a genuine gravitational wave and not something else. The disturbance was too small to be measured in millimeters, or even microns. The disturbance was smaller than the width of a blood cell. Way smaller, in fact. Smaller than any virus. Smaller than even an atom. It was smaller than 1 proton from the nucleus of an atom. In fact, the disturbance was only 1/10,000th the width of a proton. That was a mighty small disturbance in the force. But why is this even important in the first place? For starters, it has given us real data to compare to the theory of general relativity. Also, we can finally see things that don't emit any form of visible light, like black holes, which light can't escape, or other things that we haven't even discovered yet. Also, gravity promises to be the critical link between quantum physics and normal physics.